Okay, so welcome to lecture number 11. So today we want to start talking about neural networks and deep learning. And maybe most of you, because you are maybe interested in this topic here, machine learning, you already read a little bit or you saw maybe some YouTube videos or whatever on this topic. So maybe some of you have some basic idea what this means, but I will not assume that you know anything on this topic, and therefore today it will be really basic, and I just want to introduce the basic vocabulary you need to know, and then next time we will start um, doing it a little bit more seriously and talk about how to train a neural network. So as always, I will show this slide here where we have this overview. So at the end of last year, we did some example here for unsupervised learning, where we did this k-means clustering, and which is also part of your homework. And we also did a little bit reinforcement learning, where we talked about this Q-learning. And for this Q-learning, there's actually also a deep Q-learning version, which is somehow combining this Q-learning and this thing we will talk about today. So today we will go back to supervised learning. So there will be again a supervisor, meaning we will have some trainings data where we have some features and some labels. So this is what we started with. So we did this regression thing, this linear regression and this logistic regression. And the plan for the remaining 4 lectures is that today we will talk about the basic definition of a neural network. And then next time we will talk about how to train them. And then maybe after this, we will consider more complicated neural networks. And then at the end of the lecture, I maybe also want to do some examples where we actually use some implementation. And there's this famous package for Python, also for JavaScript, which is called TensorFlow. So I want to do some examples using already built library, so we can actually do some series examples. Because so far, if you implement everything by ourselves, then maybe the examples we do, these simple email spam filter and so on, maybe they are a little bit too simple. So maybe in the last lecture, I will also do some examples using this library TensorFlow. Okay, and also for this topic, I mean, there are millions of nice sources for this, but the one I can recommend, and which is also doesn't take so much time, is this video by, so this is really a basic introduction into the topic of neural networks, and by this really nice YouTube channel, 3 Blue, 1 Brown. So there you can see a lot of math videos, and he has a lecture series on this topic. So I think there are 3 or 4 videos on this. So if you have time during the weekend or in the evening, you should really watch this. And then there's also this here, which is called Neural Networks from Scratch. So there's also a YouTube series and also a book where this guy explains how to implement a really simple neural network from scratch in Python. Okay. But if you enter neural networks in YouTube, you will find a lot of nice videos, but I can really recommend this one here. So, so what is the basic idea in this topic? So in general, what we want to do, or what we also wanted to do before, for example, in this linear regression case, we wanted to approximate some functions. For example, in this linear regression case, we wanted to find a function from Rn to R. But now in general, what we want to model or to approximate are functions from Rn to Rm. And what we will consider in this course are so-called multi-layer, fully connected feed-forward neural networks. So when I say neural networks, I usually mean this. And maybe this, if you don't know anything about this topic, maybe this sounds quite complicated. But multi-layer will just mean that we have multiple layers, whatever this means. Then fully connected just means that that every circle here has an arrow to all circles in the next layer, and we will talk about this. And feed forward means we will here just have arrows in this direction. So because of these words, you already see that there may be also other types of neural networks where you can also have arrows in the other direction and so on. But if you start with this topic, then these types of neural networks are the most simplest one. And this is what we are going to talk about today. And actually, we already saw some kind of example of a neural network, but in a really, really simple form. But it already contains the main ingredients for a neural network. And this is what we called a logistic regression. So recall, we had this example of hours of studying, and we wanted to predict if we pass an exam or not. So we had some trainings data here. So we asked some students how many hours did they study, and then we asked them if they passed an exam or not. So for example, here we have these 5 examples of students who studied less than 11 hours and they failed. And then here some students who studied longer. Maybe this guy here is smart. He just studied 9 hours, but still passed. And then we had this. And what we wanted to do is we wanted to find a function which as an input gets hour of studying, and as an output, we get a value between 0 and 1, which gives us the probability of passing an exam. So we wanted to find this, this orange line here. And for this, we created, so we wanted to find this, what we called hypothesis. So this was a function which depended on some numbers, theta. So theta here was a vector. So x was a vector in R D. So in this example, D was 1. So D was the number of features. And actually, this was not just D, but it was D plus 1, because we introduced this x0, which we always set to 1. So I will write this again because we will rewrite this in a different way on the next slide. And this theta here, these weights which we wanted to find, so these were also a vector of size d plus 1. And then the hypothesis in this logistic regression case was that we multiply theta with this x here. So this here just meant that we have theta 0 times x0, which is 1, plus theta 1, x1, up to theta d x d. And then we plug this number here into this sigmoid function, or this logistic function s, which was given by this, so this s of x was 1 over 1 plus e to the minus x. So we plugged this here into this s. And then this gave us this curve. And then what the task was, given some trainings data, like in this example here, we wanted to find the best theta, so the parameter. And for this, what we did, we considered this log likelihood. And we want to maximize this by using gradient ascent. Or what we also did in this linear regression case, we had a cost function which we wanted to minimize. But maximizing functions or minimizing functions is basically the same. So for example, we could also minimize the negative log likelihood by using a gradient descent. But this was the basic idea that we had. We calculated the gradient of this log likelihood, or of this cost function or loss function, and then we went into the direction of the gradient to maximize the value of this function for this theta, or in this case, yeah, we wanted to maximize this. Okay, and this is actually it already all ingredients we want for neural networks are contained here, because here's we have a so-called linear part. So this here is just multiplying two vectors with each other. So this here is something linear, and we plug this linear part into a function here, into a non-linear function. And so let me rewrite this now using a little bit a different notation. So the input, so we have as an input a vector. So now let's say instead of D, we will now use N. So this is just a different name for the number of input elements. And what we do is so if we call this X, we multiply X with some weight, and then we add some number B. So this here in the old notation, so this, first of all, this W is here a vector in Rn, and this B is a number. So in old notation, so I just want to introduce the new notation, because this is a quite common notation here. So in old notation, this W is just the theta 1 up to theta D, so N equals D, and this B is just theta 0. And so this here is, so we take this these N values, and we plug it in here, and this is what we call linear part. And the output is we plug this linear part into this S, and this S here is called we will call an activation function. Yeah, and there's some notation. Or maybe I will leave this out. Okay, and or maybe I will write this. So here the content of this place here is we have some W, which is called the weight. Then we have some number B, which is called the bias. And we have a function S. So S in this case is a function from R to R. In this case, we use this sigmoid function, and this we call an activation function. And this here will be an example of a so-called neuron. So we have some input, and the neuron, the content of the neuron is we have some weight, some bias, and some activation function. And the output of the neuron is we plug this linear part into this activation function. So the output is again a number. Yeah, in our example with the hours of studying, the N was equal 1. So here we just had one input, and we just multiplied with a number and add a number and plug this into this S, and the output was just a number between 0 and 1. Okay. So this here we will call a neuron. And what this basically is linear part plus activation function. And what do I mean by activation function in this case? This is just a function from R to R. And in our logistic regression case, this activation function was just this sigmoid function, 1 over 1 plus e to the minus x. Yeah, so this is now just naming things. So a neuron is linear part plus activation function, and linear part consists of a weight vector and a bias, which is just a number. And this neuron can have an input. In this case, it's a vector of size n. And then what it does is it creates this linear part, and then it plugs this linear part into this activation function, and then this neuron produces a new number, and this is the output of this neuron. Yeah, and therefore this logistic regression, so this here is now an example of a really stupid neural network with one neuron, and this linear regression is therefore an example of a neural network. But at this place, it's not clear why, I mean, now we didn't define what a neural network is in general, so let's make it a little bit more complicated. So at the beginning of this course, I talked about this classification of this image classification. So here are some pictures of cats and dogs. And we talked that maybe in real life, you want to implement some machine or some software which can recognize if a picture contains a cat or a dog. So, but as I said, what we are interested in are functions from Rn to Rm, but a picture of a cat is not an element in Rn. So first, we need to convert a picture into something we can calculate with. And the idea in general is that a picture, so for example, if I have a picture of a cat, so let's say I have a picture of 100 by 100 pixels, and a pixel, so 1 point in this picture. So usually if we have 3 channels for the color of a picture, so usually a pixel corresponds to 3 colors, red, green, and blue. So therefore, in this case, what I get as an input are, so in this case, I can define n to be 100 times 100 times 3. So in this case, I have 100 times 100 times 3 different numbers. And therefore, the first step here is to create a vector out of this cat, or the picture of the cat, by just creating a vector out of this picture. And now we could plug, now we can use again the same idea as before. So we could feed this into a neuron where we have some linear part. How should I? So here I have some linear part W, and maybe some activation function. So instead of S, I will use sigma. So this is a common notation for, maybe that's not a beautiful sigma. And then the output here will be a number, namely the sigma times the linear, where I plug in the linear part into the sigma. Oops. So for example, the sigma could be this sigmoid function or some other function. And yeah, and then as before with the example with hours of studying and passing, we could train this neural network here by taking a lot of pictures of cats and pictures of not cats, and then feed this thing here and maybe use this gradient ascent or descent to find these numbers W and B. But first, I also want to use some notation. So the linear part here I will denote by that, and I will use these brackets Z1, I will define to be W T X plus B, and this output here, after plugging it into the activation function, I will denote by A1, 1. And this here will mean, well, I didn't define what I mean by a layer, but here we will say that this is the first layer, and later we will add more layers. So the upper index will correspond to in which layer we are. And the lower index here means which neuron in this layer. But in this case, we just have one layer and one neuron. So here, this notation is maybe just confusing now, but I just want to make sure. Lower index. So this is now just notation, and that linear part and A is the output. Yeah. So in this picture here, we could, with the same method like we did with the example with studying for an exam, we could train this thing here by maybe having millions of pictures of cats, and we could maybe get these numbers W and B. Okay, but now the thing is that this is just a binary classification, and maybe we wanted to make it more complicated. So maybe we want to see if a picture contains a cat or a dog or a tiger or something else. So in this case, if we do this here, we can maybe just decide if a picture contains a cat, yes or no. But we can maybe not decide if the picture contains something else. So therefore, the next naive approach to also include dogs would be to maybe just also add a second neuron for the dog. So we can have again a picture, make the picture into a vector. And now, as before, we can make a neuron here, where we plug this thing here. So somehow the cat neuron. So the cat neuron will give an output, a 1, 1. Or maybe let's directly write it inside here. So this a 1, 1. And this number here, so this contains some W and some B, which we can train with cat pictures. And the output here will give us a number which decides what is the probability that this picture contains a cat. But now we also want to decide if there may be dogs inside. So maybe we just train another neuron where we also feed things in here. A1, 2, which maybe then decides if the picture contains a dog. Yeah. So, so now we see, I mean, with the same idea as before, but instead of just having one neuron, we now have two neurons, and the output of this whole thing are two numbers. So if I put a picture into this machine, then I will get back two numbers, and then maybe I look at the larger number, and then the larger number will tell me if this is a cat or a dog. And maybe if both numbers are around 0, then maybe there's no cat and no dog in this picture. But it turns out that if you do this, then actually just using these two neurons in this complicated case here, I mean, pictures, we already saw in the example before, if I would just take 100 by 100 size pictures here, then I already have a lot of numbers, that this actually wouldn't give really nice results, because this simple idea that, I mean, a cat is a really complicated object, just using these numbers W and B and one neuron to detect a cat is a quite challenging task. So the idea for neural networks is not just to have this one layer which is doing everything, but to include more layers where at each layer you maybe decide, maybe you can see just one specific part of the picture. So maybe let's try to make this clearer. So let me say, so here again I have some cat or dog or whatever this is, and then again I can make a vector here, and maybe let's say I have maybe 3 neurons here, so where I feed this in, and maybe let's put 2 neurons here where I maybe give the output of these old neurons will be the new input of these neurons. And what you can maybe think of is that these neurons, this neuron is maybe just responsible for detecting certain edges. So for example, could be that this neuron detects some edge like this, so maybe some certain parts of the picture, and maybe this here could detect an edge like this, or maybe this can detect an edge like this, and so somehow it's detecting something more simple than a complete picture of a cat or dog. Maybe one neuron is just responsible for detecting a certain shape in a picture, a circle or an edge or something else. And then in this second layer, the input is not a complicated picture, but the input now here is just 3 numbers, which somehow say I have a lot of this edges and I have this edge. I mean, this is now really boiled down really simply, but maybe then this neuron here is maybe responsible for detecting ears, and maybe this neuron here is responsible for detecting a mouth of a cat or a nose, depending on what the input here is. And then maybe this could lead maybe to 2 neurons here, where we then in the end can distinguish if I have a cat. Well, I don't know how to draw a dog. Well, but the input of these neurons are now these basic shapes, and then it's well, these are terrible pictures, but I hope the idea somehow becomes roughly clear. And for each of these neurons, we have the same mathematics as before. So we have some input. So here at the beginning, all these neurons, they get all these n numbers. So this is what we mean by fully connected, that this neuron here gets all n numbers here. So it gets a vector of size n. And so then there will be some linear part, which in layer 1, the first neuron will have some linear part, and it will have some activation function. And usually the activation function will be fixed for a layer. So here, if we plug it into an activation function, which I should also give an upper index for the layer, this will be then the output of the first neuron in the first layer. So here I will get some number A11. Here I will get some number A12, and here I will get some number A13. So And then I can view this again as a new vector with 3 entries. And then the game starts again. This here gets a vector of size 3 in this example here, and it will produce a number in the second layer. So this here is first layer, second layer, and here the first neuron in the second layer, and here the second layer in the as a second neuron in the second layer. So these will be some numbers. So this here is again a vector of size 2, and this will get feed here into these. So here we will get some number A3, 1. So this will be the third layer, which, because it's the last one, we also call then the output layer. So in the end, we will get 2 numbers, A31 and A32. And this here is the input layer. I mean, this here we could also view as the vector A0, which has entry A01, A02, and so on. And these layers here, the ones in between these input layers and output layers, they are called hidden layers. So because what I explained here, I mean, this was just, I mean, we could implement this now with these 3 neurons and these 2 neurons here, and then maybe feed this machine with a lot of trainings examples. So in trainings example, in this case, would consist of a picture, which is a vector, and an output vector, which if I give a dog picture here, so for example, one input would be this dog here together with the vector 0, 1, or this cat picture here with the vector 1, 0, because the input is this here and the output should be, in this case, a cat, and in this case, a dog. And then we could feed this thing here and train this, where, of course, we didn't talk about how to train this, but let's assume that this is possible. Then internally, this neural network will learn something like this, but actually we have no control, or we don't see what these neurons actually do. So here in this case, that maybe the first layer is responsible for basic shapes like edges. So this is just a guess. And then the second layer is responsible for more complicated shapes. But this is somehow hidden for us later. So this is also why this is called a hidden layer, or hidden layers. And in this case here, we have 2 hidden layers and the input and output layer. Okay, are there any questions so far for these notations? So the linear part, well, I will make it clear soon, but are there any questions for these indices? Okay. So then again, some notation. So I mentioned this word activation function, and so there's no precise definition for an activation function, except that it should be a function from R to R. But there's a finite list of functions which are usually used in practice. Because later when we want to use this gradient descent, then we want some activation functions where we understand the derivative and where we can implement this gradient descent in a nice way. But what you need to have in mind, activation function is just a function from R to R. So for example, this sigmoid function. And a neuron, which in this picture is one of these circles, so this just consists of a weight vector, so some numbers for the weight, and one number for the bias. So this is what we before called theta. And it also consists of an activation function. And this is all a neuron has. And we can feed a neuron with, in this case, if the weight vector here has size n, then the input of this neuron has n inputs. And the output of a neuron is always one number, namely the number we get after plugging this linear part into this activation function. And then a layer is a collection of neurons which are not connected to each other. Okay. And yeah, so and the first layer is called the input layer, and the last layer is called the output layer, and the layers in between are called hidden layers. So if we want to implement a neural network, we need to think about what do we need to save, or what is the content of a layer. So if we have R layers, so in this picture here we have, well, maybe the input layer we always say is layer 0, but for example here in this picture maybe R is 3. So for each, so this should be an I. I thought I changed this. Oh, I just changed it in the slide afterwards. Okay, so for each layer, we have a weight matrix. So why a matrix? So before what I said was that for each neuron, we have a weight vector. So in this case here, for this neuron, we will have some weight vector W. So we will have some, so WI1, but this will be a vector, and here we'll also have some vector, and here we'll have some vector. So this layer here will have a weight matrix where these vectors here are the columns or the rows of this matrix. Yeah, so so for example here, so let's consider the first layer here. What is W1? So W1 will be, so here I say it's an M by N matrix where N is the number of inputs. So in this case here I have, for each neuron I have N inputs. In this case this will be an M by N matrix, and M is the number of outputs. And here in the first entry I will have the vector, the weight vector of the first neuron here. Yeah, so I said for each of these neurons, I want to save a vector, because here the linear part of this, the Z in the first layer, first I will multiply with the input X. I will multiply with some transpose of a vector of size n. But this here I can now just say this is, in this case here, this guy here. And if I, and after this I want to add some b, let's say B1. So these vector times vector plus vectors for each of these neurons, we want to write as a matrix times vector, vector times vector plus number. We now want to write for one layer as a matrix times vector plus a vector. And so therefore for each layer, will have a matrix where these columns are exactly these, in this case now row vectors. So instead of taking the transpose of a column vector, I will now write it as a row vector. And instead of just adding a number here, I will consider all of them at the same time. So the first number here will be the first entry of this BI. So this here is the first entry of B1. And this here the W1 is the first column of this W1 here. And therefore the linear part of these guys will be also a vector where each entry then gives the linear part of these neurons. Yeah. Is this somehow clear? So instead of collecting for each neuron now a vector, I want to have a package for the layer. So if I would implement it in Python, the information for one layer is a matrix, which corresponds to these weight vectors, and a bias vector, which corresponds to the different biases, which are numbers. So here this B1, the first number B11 is the bias of the first neuron up to B1 M. So here M in this case. I've written it here. So the M is the number of neurons in this layer. So in this case here, M is the number of neurons here. Yeah, therefore for each of these neurons, I have a bias. And for each of these neurons, I have a weight vector. And to get the linear part for each of these things here, I just multiply this matrix with the input vector here plus this bias vector here. And and then to calculate the output, I think I have it on the output vector in this case will then be, I apply the sigma to each of these entries, that I1 up to sigma that I m. Yeah. Well, are there any questions? I didn't just see two of your faces, so I don't know. And they are not smiling, so I assume maybe I made some mistake or there's something not clear. So I just want to make sure that the notation is clear, because this we will use later in the course. And so far, I think it's just really notation. And maybe the indices are a little bit confusing, but I mean, these brackets correspond to the layer, and the lower index is always which neuron. And a layer, so this here is one layer, and for one layer, I need to save a weight matrix, a bias vector, and then to calculate what I will plug into the next layer, I will need to first calculate the linear part of this layer, and then the output is given by applying the activation function to each entry here. So the output will be again a vector, and in this case the vector will, well, in this case it's a vector of size m, because m is the number of neurons. And then in the next layer here, I will have a new matrix W2. And to calculate the linear part, I will multiply W2 with in this case, A1, and then add B2. So here, and that's why I wrote this here, this X here, which I multiply with this matrix, is always the output of the layer before. And in the first step, the output of the layer before is just the input vector. So that's why this, this input vector we can always somehow see as A0. It's the output of the 0 layer. And then the next input will be A1 and so on. And in the end, the output will be AR, a vector, of, or maybe, so this is maybe not good here. This M is not this M here. So in this description here, I just consider one layer and call the number of neurons N. Of course, these layers, they can have different number of neurons. And here in this picture I stole from the internet, the number of output things here is also M. Okay. I don't know why I have this slide doubled. Okay, and now, so these activations functions, so I said they're just functions from R to R, but there are some standard examples which are used. So the idea and why this is called activation function, so maybe let's go back to this here. So I mean, why is this called neural network? I mean, the naming comes from neuroscience, where, well, I don't know anything about neuroscience, but there's a notion of a neuron which somehow can fire or not, so you can turn it on or not. And somehow this activation function is, so you put this linear part into this activation function, and for example, the sigmoid function, which was between 0 and 1, somehow is on or not, or gives a probability of being on or not. So somehow this activation function tells us if this neuron is turned on or not. So for example, here, the activation function, this should give a number 1, for example, if this detects an edge like this. And this here will maybe fire if this detects an edge like this, and this maybe if this sees something like this. So the idea is that these neurons, maybe really rough idea, are responsible to detect something, and then their output will tell the next layer if they detected this thing or not. And therefore this activation function somehow tells us if this neuron was activated or not. And so there are several standard examples for activation functions, and maybe one really often used one is this here, the so-called rectified linear unit, and the name is much more complicated than the function itself. So what this basically just is, so this is a function from R to R, and this just checks if the number is positive or not. So if you draw the function, this ReLU here, then this is the maximum of 0 and x. So this just means if x is negative, then this function is 0. And if x is positive, then this is just the function, the identity function. So somehow, if you use this as an activation function, then somehow if the linear part of the neuron is negative, then the output is just 0. So this neuron is not activated. And if the output is positive, then depending on how much this number x is, the output will be larger or smaller. So this is just this simple function here. And the other example, this sigmoid function we had before, was something like this between 0 and 1. But you can also see here there's a Wikipedia page, for example, for activation functions, where you see several different examples. And here you see also a column for the derivative of this function, because this will come later into play when we will be interested in the gradient descent and how to train our neural network. And now one question here for you. You can think about this question. So why would it be not so useful to use the identity as an activation function? So why not just use the linear part? I mean, the identity map is also a function from R to R. And if you think about this, so maybe let's go back to the example here. So if you would just use the identity function here and you write everything out, so then the output here would be basically just multiplying with the matrix and adding a vector. And if you combine everything, you actually would see that you don't need different layers. So if the activation function is just the identity map, then you could just directly write everything as just one linear part. So this would then in the end would be just what we did at the beginning, namely this linear regression. So therefore this activation function, the main point here is that this is in the most cases not linear, because otherwise you will just get back this linear regression which we did at the beginning. Okay, and yeah, so in the end, I just wanted to make these notations clear by really one explicit example. What is if we have a neural network with 4 layers, which I basically almost wrote down. So let's maybe, so we have the input layer, A0, oops, A01. So this is what we call X input. And let's say we have in the first layer, we have 3 neurons, A11, 2, 3. And so we feed this X into this. So this here is the first layer. So what do I need to save for this layer? How much information? So what in this case, so let's say this input layer here is in R. Let's say this input vector is R5. So what do I need to save for this layer here if the input is R5? So first of all, I will have a weight matrix. So the weight matrix of the first layer. And this weight matrix, maybe I can write as a matrix. This here contains for each neuron, it contains a weight vector. So this matrix here will have 3 rows. And the number of columns is because I want to multiply this with the input vector. This is a vector of size 5, and therefore the number of columns need to be 5. So here I have 3. Maybe I just write it down. This here is a matrix. It's a 3 times 5 matrix. And the bias, well, for each of these, I have a number. So this will be a vector of size 3. Yeah. And then so this output vector So the output vector A1, which as entries has A11, A12, and A13, this is sigma. So sigma is the activation function of this, let's say sigma 1 of that 1, 1, sigma 1 of z 1, 2, sigma 1 of z 1, 3. And maybe let's write this as sigma of sigma 1 of z1. So here I apply so this is not a good notation. So this is now maybe let's define it like this. What I mean by this, I apply a real function to a vector, and by this I mean I just apply it to each component of this vector, and therefore this is just sigma 1 of this weight matrix. So the linear part is given by the weight matrix times x plus the bias vector v1. Yeah. But anyway, so this is here just a calculation. The stuff we need to save are here these 15 numbers and these 3 numbers here. So this layer to store the information are 18 numbers plus the information what activation function we have. And then we can have maybe in the next layer, we maybe have we have maybe 2 neurons. So this here is now layer 2. So what in this case is W2 and what is B2? So what is the size of the weight matrix in the second layer? Someone? Chat or voice? Or Menti if you're shy.
2 times 3.
Yes. So this is a 2 times 3 matrix, right? Because I will have, for each neuron, I have a row, and as an input, I will have a vector of size 3, namely this vector here, this A1 will be the vector I will multiply with this matrix. And here the number of biases is 2, so here I have a vector of size 2. And then maybe in the end, I will have 1, let's say the output layer is maybe this. So here, let's say the last W. And of course, I have some bias here. So maybe I have some sigma 2, which is maybe this rectified linear unit or the sigmoid function. And here, maybe I also have some sigma 3. And here, in this case, the B is just a number. And this here is 1 times 2 matrix, meaning it's just a row vector. Yeah, in this case, the output of this neural network will be a number. So for example, this could be a cat detector where maybe here we have these simple shapes and here ears and mouth, and then output will be what is the percentage that's the input. Well, maybe a picture of 5 pixels is maybe not so interesting, but what is the percentage that this is a cat or something else? Okay, and so maybe the last part is a little bit silly, but I would show you how to do this calculation in Python. But this is exactly now what we did here. So I will change the screen now. So this is now how you could calculate the the stupid neural network I just wrote down. So as an input, I take a vector A0, which in our case was a 5x1 vector. And this function here just gives a vector with the random values. And I mean, Python or this NumPy allows you to subtract the number from a vector, which of course mathematically is not defined, but this just means that each entry gets subtracted by 0.5, because what I want here in this case, this usually gives a number between 0 and 1, but I also want negative numbers. So here, this will be a vector of size 5 with entries between -1/2 and 1/2. And for example, this rectified linear unit, which we you will use here as activation function, is this stupid function here. So this maximum will not give the maximum entry. So there are two functions in NumPy. So if I have a, maybe let me show you an example here. So for example, here I have this vector, vector of size 5 with these numbers. Now they are all between 0 and 1. So if I subtract here 1/2, you see there will be between -1/2 and 1/2. And if I would do this here, np max A0, yeah, so for example, this command would give me the maximum entry, but if I use the command maximum, then this will give me a vector where in each part I check if the number, I will take the maximum of this number and 0. So this here is then exactly what this rectified linear unit does. So here's all these values which are negative, they will get sent to 0, and these numbers which are positive just stay the same. So so there's this. So therefore, this is what we want. So this we will use as a sigma. And here the first layer, this W1, the weight matrix, as we discussed, is a 3x5 matrix. I will also again take just random values here. And the bias, we have 3 values because we had 3 neurons in this layer. And then the linear part is, here this dot is just the multiplication of the matrix with its vector. So this is the input vector, and we add the bias. And then the output is we apply this, this activation function. And this here will be then the input of the next layer, where in this case we had 2 neurons. So we have a 2x3 matrix. 3 was because here the output is A1. Maybe I can, oh, maybe just, so here this A1 is this vector of size 3, and therefore here we have 3. And yeah, and the linear part in the second layer is this here, where we multiply with the output of the layer before, and then apply activation, and so on. And then here in the last layer, we take the output of the layer before. And therefore here, we will, in this case, we will either get, because the last step, the activation function is this rectified linear unit. So we will either get a number 0, or we will get maybe a positive number, right? So either it's maybe a negative number, which maybe says it's really not a cat, but if it's positive, maybe it's how certain it is that it's a cat. So yeah, so every time I play this, I will get some new values here, because in every step I get some random weights and biases here. And yeah, and that's basically all for today. So of course now the interesting question is, how do we find the good values for these weight and biases. And the idea will be, again, to define a cost function, which we want to minimize, and we want to minimize using a gradient descent. But we need to take care of these different layers. And there's a thing called a back propagation, which we will use to apply this gradient descent to train our model. And this we will do then in detail next time.